we have written the governing equation in dimensional form. So, now let us write this stream function and vorticity equation in non-dimensional form. So, our governing equations in dimensional form dimensional governing equation we have written del 2 psi by del x square plus del 2 psi by del y square is equal to minus omega and u del omega by del x plus v del omega by del y is equal to nu del 2 omega by del x square plus del 2 omega by del y square. Okay. So, we will use these non-dimensional parameters as say characteristic length we will take as L, okay, and characteristic velocity we will take as u, capital U. So, you can write the non-dimensional form in star quantities. Okay. So, u star is the non-dimensional velocity, you can write u by capital U, v star is non-dimensional v velocity. So, v by characteristic velocity u. Similarly, x star is the length. So, x by L, y star is equal to y by L, and your psi star, okay, you can write as psi by u into L, and omega star you can write omega L by u. Okay. So, these are the non-dimensional parameters. So, these now you substitute it in the dimensional equation and rearrange it, you will get the non-dimensional form of the governing equation. So, in non-dimensional form of governing equation, so I am not going to derive, just I am writing del 2 psi star by del x star square plus del 2 psi star by del y star square is equal to minus omega star. So, these are non-dimensional psi and non-dimensional omega, and similarly u star, okay, and u star is nothing but your u star is nothing but del psi star by del y, and v star is equal to minus del psi star by del x star. Okay, this is also star. So, you can write u as del psi star by del y star del omega by del x. So, this is also star because non-dimensional equation, and v star is minus del psi star by del x star, okay, and del omega star by del y star, and you will get the non-dimensional number as Reynolds number, okay, 1 by R e del 2 omega star by del x star square plus del 2 omega star by del y star square. Okay. So, this is the vorticity equation in non-dimensional form, and in the right hand side the diffusion coefficient you are getting as 1 by R e. So, earlier it was nu which was kinematic viscosity, now using non-dimensional parameters now you are getting 1 by R e. R e is equal to Reynolds number is equal to, here you are getting rho u L by mu or u L by nu. Okay. U is the characteristic velocity, L is the characteristic length, and nu is the kinematic viscosity. And you know what is Reynolds number? Reynolds number is the ratio of inertia force to viscous force. So, this is your Reynolds number. Okay. So, now for this lid driven cavity problem, we will take the characteristic length as L, side of the cavity, and characteristic velocity will take as the lead velocity u. So, with that if you non-dimensionalize it, so you will get this non-dimensional equation, and if you discretize it you will get the discretized form of the governing equation. Only difference will be that wherever nu was there you just put 1 by RE, okay. Then you will get in non-dimensional form this discretized equation. And when we will consider the flow between parallel plates, so that time we will take h, height is the non-dimensional characteristic length, and inlet velocity u as characteristic velocity, okay. So, accordingly we will get the Reynolds number. So, in the Reynolds number for lead driven cavity problem, lead driven cavity, Reynolds number is your u L by nu, where u is your lead velocity and L is the side of the cavity. And for flow between parallel plates, okay. So, you will get Reynolds number as u h by nu, okay, where h is the height of the or the distance between two plates and u is the inlet velocity, okay. So, now we will show the code of this lead driven cavity problem, okay. So, whatever we have discretized the equation as well as the boundary condition. So, that how you can write the code, that I will show, then I will show some results. So, this is the code you can see. So, this is general header file, you just include it. So, this is the main program. For writing the output, we are opening one output file. So, some integer I, j, mn, mn, p we are just defining double dx, dy, xy. We are taking number of points along x direction 301 and number of points along y direction 301. So, total number of interior points will be m minus 2 and n minus 2, and delta x delta y will be 1 by m minus 1 and 1 minus n minus 1. So, we are taking lead driven cavity, okay, and this is your velocity u, okay, and we are taking in non-dimensional form. So, we are taking 1 as side, okay, and u is equal to 1. So, your u is equal to 1. So, accordingly we have solved the problem for Reynolds number 100,000, okay, 400. So, this we have taken. So, now you can see beta just delta x by delta y we have defined, and Reynolds number 100 we are giving the input. So, psi omega u v, this just array we have defined here. We are using previous value of psi and omega just to calculate the error, and now we are initializing at the interior point, and at the boundary we are writing the boundary conditions for velocity and the stream function. So, now we are giving the boundary conditions for u and psi. So, this u and psi we are giving. After that, from psi we will calculate the boundary conditions for the vorticity. So, this you can see. So, all over we are giving 0 because all the in all 4 walls we have put psi is equal to 0, if you remember, okay. So, psi is equal to 0. So, psi is equal to 0. So, that we are putting, and on the top wall you have velocity 1, u I j is equal to 1, that we are defining, and accordingly all everywhere it is 0, and all interior points also we are putting 0, okay. So, you can see. So, all interior points psi also we are putting 0, and for omega, so whatever boundary condition today we have derived, okay. So, those boundary conditions just we are writing here, and before starting the solution we are applying the boundary condition from the u and psi boundary condition. So, you can see that from psi we are just writing j is equal to 0. So, you remember here we are starting from j is equal to 0 to, okay, j is equal to n minus 1, okay, n minus 1, and I is equal to 0 to I is equal to m minus 1, because during derivation we have written I is equal to 1 to j is equal to m, okay, sorry, I is equal to 1 to m and j is equal to 1 to n. As we are starting from I and j 0, so we just minus 1 we have done from the I max and j max. So, it is m minus 1 and n minus 1. So, you are see that j is equal to 0, okay, j is equal to 0 is the bottom wall. Okay. So, you are putting it and this is your j is equal to n minus 1, okay, j is equal to n minus 1. So, you can see n minus 1 means it is on the top wall and top wall you have velocity u. Okay. So, this is the u I j. So, u I j is 1 in this case. So, this we have written, and for I is equal to 0, I is equal to 0 means you have left wall. So, this is the left wall omega boundary condition, and I is equal to m minus 1, it is right wall boundary condition, and all interior points omega is equal to 0. So, this is the boundary condition and initialization I have done before going to the solution. So, now we have used Gauss-Seidel method. So, just only one unknown omega I j and psi I j, and we have used the best available value of psi and omega while calculating this omega I j and psi I j. So, for calculating the error, you can see that we are storing the psi I j and omega I j in the previous value, okay, and then we are solving for stream function. Okay. So, for all interior points. So, j is equal to 1 to n minus 1, I is equal to 1 to m minus 1. Okay. So, these interior points. So, psi I j. So, this is the if you remember, we have discretized equation psi I j is equal to 1 by 2 into 1 plus beta square psi I plus 1 j plus psi I minus 1 j plus beta square psi I j plus 1 plus psi I j minus 1 plus delta x square omega I j. Okay. So, this is the equation, okay, discretized equation. So, that we have written, you see this is your 1 by 2 1 plus beta square psi I plus 1 j plus psi I minus 1 j plus beta square psi I j plus 1 psi I j minus 1 and plus delta x square omega I j. So, this we are calculating the psi value at all interior points, and you can see that these are coupled equation, the vorticity equation as well as your stream function equation. So, after converging it after solving for all interior points, then we are solving immediately this vorticity at all interior points before going to the next iteration. So, you can see this also we are solving for vorticity. So, in the vorticity you see omega. So, this is the discretized equation if you remember. So, whatever we have derived, okay, but here nu just you put 1 by R e, whatever equation we have written. So, nu is equal to 1 by R e if you put, then you will get this equation as omega I j is equal to 1 by 2 into 1 plus beta square, okay, and 1 minus psi I j plus 1 minus psi I j minus 1 beta by 4 nu. Okay. So, nu 1 by R e we are putting. So, this is your equation omega I plus 1 j plus 1 plus psi I j plus 1 minus psi I j minus 1, okay, beta into R e by 4 omega I minus 1 j plus 1 plus psi I plus 1 j minus psi I minus 1 j, okay, then Reynolds number by 4 beta square omega I j plus 1 plus 1 minus psi I plus 1 j plus minus psi I minus 1 j, Reynolds number by 4 beta square omega I j minus 1. Okay. So, this is the discretized equation in non-dimensional form. So, Reynolds number just wherever nu was there we have put 1 by R e. So, you can see that we have written. So, you see 1 minus psi I j plus 1 minus psi I j minus 1 beta into R e by 4 into omega I plus 1 j. Similarly, this is for omega I minus 1 j. Okay. So, all these we have just written the for all interior points and we are calculating omega I j. Okay. So, in single loop now we have calculated the psi I j and omega I j because both are coupled. So, next we are actually applying the vorticity boundary condition again, okay, because psi is applied. So, omega boundary condition will be updated. So, we have updated the boundary conditions, then we have calculated the error. Okay. So, error psi is equal to error psi plus psi I j minus psi previous I j whole square. So, this is the summation over all the grid points we are doing. Okay. So, then after coming out of this loop, just we are dividing by total number of grid points and we are making the square root, and error for psi and error for omega we are calculating, and also we are calculating the iteration. We are printing error psi error omega with iteration and going to the next iteration, then we are checking the condition. Okay. So, this error psi and error omega both, if it is satisfied 10 to the power minus 8, then it will actually if it is greater than 10 to the power minus 8, okay, error for psi and error for omega. So, if it is greater than this, then this iteration will continue. If it goes below 10 to the power minus 8, then it will come out of the loop. That means your solution has been converged. So, once the solution is converged, then you can calculate the UV at all points, including boundary points you know. So, all interior points you calculate and you print this x, y, u, v, psi, omega to just plot it. Okay. So, now you can see the velocity vectors, streamlines and vorticity contours for different Reynolds number. So, Reynolds number 100 and Reynolds number 1000. So, these are the velocity vector. UV we have calculated. So, this UV from UV we have shown the velocity vector. These are the stream function contour actually. So, these are stream function contour. So, you can see. So, we have given 0 at the wall, right. So, 0 at the wall we have given. So, accordingly you can see that this value is increasing 0.002, 0.02, 0.04, 0.06, 0.08. So, sorry, it is actually, so you can see psi is equal to 0 we have put in all walls. Okay. So, this psi is decreasing minus 0.002, minus 0.02, minus 0.04 and minus 0.1. Okay. And now you can see that once the lead is moving this side, okay, so this is your velocity vector. So, one primary vortex is generated here. Okay, this is your primary vortex. So, it is primary vortex is generated and some secondary vortices are also generated at the corners. Okay. If you go Reynolds number 1000, so the primary vortex center has been shifted downward direction, okay, and there you can see this secondary vortex size has been increased. Okay. So, here it was like this you can see, but here the size is increased and this is the vorticity contour. Okay. So, obviously you can see near to the wall you have maximum vorticity, okay, the value you can see, okay, you have maximum vorticity near to the wall, okay, because velocity gradients are more near to the wall. So, you will get more vorticity near to the wall. So, this way you can calculate the stream function contour as well as the vorticity contour and velocity vector, and now you got the results. So, to know whether the results are correct or not, we have compared these results with some benchmark solutions. So, there is a paper Ghia et al. So, with that we have compared our results. So, you can see that present case we have taken 100, 400 and 1000 and these are the lines in our simulations. Okay. So, these are the u velocity profile along the vertical center line of the square cavity. So, if you have square cavity here, so you are calculating the velocity along the vertical center line. So, along this you are actually plotting the u velocity. Okay. So, that you can see that our results are these lines, and Ghia et al. Which actually is also numerical solutions. So, that we have put with the symbols. Okay. So, you can see that these our results matches well with the literature. Here also we have compared v velocity. Okay. V velocity we have compared along horizontal center line. If it is the cavity and along horizontal center line we have compared the V velocity. So, our results with lines and Ghia et al. With symbols for different Reynolds numbers, and you can see how the velocity profile looks like. Okay. So, these are some comparison with the literature. Next, we have solved the channel flow. So, you can see so here L is equal to 6 h we have considered, h is the distance between two plates, and u is equal to 1 we have given, okay, non-dimensional velocity, and h we have taken in the Reynolds number. Okay. So, we have used grid 100 by 60, and now once you solve and with the, if you solve the vorticity discretized equation and the stream function discretized equation along with the boundary condition what we discussed for this channel flow, then if you solve this vorticity and stream function, then you will get the velocity profile inside the channel. So, these are the velocity profile I have shown. Okay. So, obviously, at the you can see that these are x equal to 0. So, that means it is inlet velocity condition, and 1 we have given, and as your x axial direction if you proceed, then obviously it is developing, you can see that these are developing, okay, developing velocity profile. Then once it becomes it comes to the fully developed region, so it becomes fully developed, and in fully developed region you know the maximum velocity will be the 1.5 times with times the average velocity. So, that we are getting. So, your inlet average velocity is 1. So, sorry, average velocity is 1. So, obviously, the maximum velocity will be 1.5 times. So, in our numerical simulations we are getting 1.493. So, you can see that here is the maximum velocity and it is parabolic in nature, and for different Reynolds number we have simulated, okay, and the velocity is becoming almost 1.5 times the average velocity. Okay. So, also you can plot the stream function for this. So, it all will be almost parallel except the near to the inlet. So, this we have solved using stream function vorticity equation. So, you can see that it is this vorticity stream function formulation is very simple to write the code and solve the problem, and but it is limited to 2-dimensional problem. But if you want to calculate the shear stress or sorry if you want to calculate the pressure difference or the drag coefficient or lift coefficients, then you cannot do just after solving this vorticity and stream function, you need also the pressure distribution. But as we derive, while deriving the vorticity transport equation, we have actually the pressure term is avoided. So, we cannot directly calculate the pressure from these equations. So, but if you really want to calculate the drag coefficient and lift coefficient, then you need to solve a pressure Poisson equation. So, this pressure Poisson equation will look like this, but we are not deriving it here, but if you want to calculate, then for this 2-dimensional situation your pressure Poisson equation will be del 2 p by del x square plus del 2 p by del y square. Okay. So, from the momentum equation you can actually calculate it. So, it will be del 2 psi by del x square and del 2 psi by del y square minus del 2 psi del x del y square. Okay. So, this is the pressure Poisson equation. Okay. So, this equation once the psi is known, then you need to calculate these gradients and you can solve for this pressure equation. Okay. So, this is the limitation of using vorticity and stream function formulations. Today we have derived the boundary conditions for stream function as well as the vorticity from the known velocity boundary conditions. Then we have shown the code for Liddemann cavity, and the boundary conditions we have derived for both Liddman cavity problem and the channel flow. And then we have shown a code for solving the Liddman cavity problem, and we have shown the results for different Reynolds numbers for this Liddman cavity problem. We solved the governing equation in non-dimensional form, and the Reynolds number comes into picture. So, here for different Reynolds number we have solved the Liddman cavity problem, and the results we have compared with the literature, and the results matches well with the literature. Then we solved the channel flow. So, in channel flow also we have shown that the fully developed condition, the velocity profile becomes parabolic, and the maximum velocity at the central line you will get 1.5 times the average velocity when it becomes fully developed. Thank you.